If I just go to mute screen.
There
No?
you go. Excellent.
Okay, very strange. Okay, so George just posed this question about, there's these different populations in space for North America where we have these, 1.7 granitoids, 1.4, 1.1, some older stuff. So what is this going to look like in hafnium isotope space? And so what we're going to do is just, one of the ways that we recommend approaching these problems is to not analyze every single grain, because that would be both expensive and time consuming, but to just analyze populations. So we're going to take a look at some of the data that was produced in our lab and try and break it down. So here's kind of what's happening, 1.8 GA. We see this vertical spread in epsilon hafnium space. Some things that lie are unsure, and some white are gold in epsilon hafnium space. And so there's vertical mixing array.
Hang on, Sarah. Audio feedback going on. Turn your volume down, maybe.
Okay, vertical mixing array. Okay, all right. Thank you guys. Okay, so let me know if it gets bad, just interrupt me. Okay, so we've got this vertical mixing array at like 1.8 GA that comes up to CHR and goes down to more evolved signatures. And so, the question, of course, is, well, where is this coming from? And conveniently, if we're just looking at the average crustal evolution line, we've got some older sources, and so we can easily invoke just kind of remelting of those sources. Okay, so if we come up to maybe 1.7 GA, all of a sudden we're sitting on depleted mantle. So here's a case where it might be appropriate to use depleted mantle extraction ages, because you're actually living on depleted mantle. So we can probably say that there's some sort of juvenile arc magmatism that's going on at this time, which is pretty compatible with kind of the North American history. Okay, so I was hoping to get this going in a quiz, but I wasn't able to get onto the polling earlier. So the question for you guys is, what's going on here? So 1.4 GA, we're sitting at like, epsilon hafnium of about +5. What are we doing here? Are we creating new juvenile crust? Are we remelting old crust? If we're remelting old crust, what's melting? So go ahead and hop on chat, and hopefully George or Kurt can read off some answers.
Yeah, let's see if we can get everybody chatting away here. Let's everybody jump in. The question is, how did you end up here? You're at +5. You're kind of in the middle of hafnium epsilon space. How did you end up there? This is your data set.
All right. Starting to get some
everybody jumping in.
Yeah. Why don't you read them off, George?
Let's get a few more people jumping in. I think we have some experts in the audience here. They nailed it right on the get-go.
The ringers.
Yeah. So it looks like there's consensus. I love it when that happens. Looks like it's maybe remelting of the 1.7, 1.8. If you follow that average crustal evolution line, it's right on that trajectory of remelting that slightly older crust.
Yep, so if you just melt these guys, you're gonna plop right down to here following this average crustal evolution line. Okay, so the next population is, of course, the Grenville population. And again, we get this big vertical spread. And the question here is melting these guys, these kind of older crust, is that sufficient to generate the spread that we see here? Can we just remelt?
Yeah, maybe the question to ask is, what else do we need to add to the system here? Yeah, here we go.
So notice that there's some populations that are living up here. If we're remelting anything out here, it's just going to be moving down in epsilon hafnium space. So we need to add some sort of juvenile components to this to get this vertical spread. But a lot of it's just remelting old crust. Okay, so my next question to you guys is, I'm trying to keep you guys awake because I know it's been a long day already and we've got a long ways to go. So trying to get you guys involved. Okay, so the next question is this. We know that a lot of times when we see these hafnium isotopic data sets, people get excited when they see what we call isotopic pull downs or excursions towards more negative, more evolved values. So what are some of the processes that might spur an isotopic pull down? What might drive an isotopic pull down? See, I teach an intro class with George right now, and we have 150 students, so I'm perfectly happy sitting here and waiting for some responses. I've gotten very good at this.
What is isotopic pull down?
Yeah, okay, so a lot of times what we see in these data sets is that they will all of a sudden go towards more negative values. They will go from super juvenile values up in positive space to more negative values. And so the question is, how do you drive that? How do you make something that is juvenile crust all of a sudden become more evolved crust or more negative isotopic values? So we've kind of already explored one of these options, right? Which would just be remelting of crust that's already there.
Jeff is offering a scary possibility that maybe it's a bad mass bias correction.
Oh, that's terrifying.
Yeah, let's hope that's not the case.
Oh man. All right. Do we have any other options, or should I just jump to my kind of interpretations?
Oh, we have a good idea. I'm not sure if Sarah can see the chat, so I'll just read off. Assimilation of older crust. Christian is offering that possibility.
Yeah, absolutely. So assimilation of older crust, remelting of older crust, absolutely. All right, I'm gonna jump to my next one, my next slide here. So it turns out that these isotopic pull downs, these deviations from more positive hafnium space to more negative hafnium space get interpreted in a bunch of different ways. And kind of one of the things that I get really interested in going through these data sets that are published is, why do people call on different mechanisms? So sometimes they're interpreted as Christian offered, assimilation during crustal thickening. It can be driven by underthrusting of isotopically evolved lower crust, so into those melt fertile regions under, say, an arc. The inboard migration of a arc into a more evolved crust, and that could be a thicker crust or an older crust, or just these vertical mixing arrays that we've already seen. So I'm going to kind of show you examples of each one and try to tune your eye to why people are invoking different mechanisms. Okay, so here's an example from Southeast Australia. This is a really cool example to me. So what they see here is along this margin from roughly 500 MA to 250 MA, they see these strong oscillations in kind of hafnium space. So, you know, at 400 and I don't know, 30 MA, they see this, what we would call an isotopic pull down. And then gradually from 440 up to 350, we see an isotopic pull up. And so the way that they interpret this data set is that these periods, these isotopic pull downs, which are also marked by a change in melt composition, mark periods of crustal thickening. And then these periods where things go towards more juvenile compositions represent periods of crustal thinning. So this is a really interesting data set that was put out by Jay Chapman in 2017. He has a follow-up paper in geology with Mihai. And what he does in this paper is he looks at isotopic trends along convergent margins. And the question here isn't through time, but is rather a spatial issue. And what he shows is that many of these apparent isotopic pull downs, these trends towards more negative isotopic values, actually are spatially controlled, such that outboard near let's say near a trench, for example, at a subduction zone, you tend to get these more positive isotopic values. And as you move inboard into a continent, you tend to get more negative values. And the way that they interpret this is essentially just, and they basically show that this has more or less nothing to do with the age of the magmatism and is entirely controlled by kind of these spatial distributions. And so the argument that they make in this paper is that that it's a spatial control on isotopic compositions, and they offer kind of two different mechanisms to explain that. One is that as you get closer to a margin, you tend to have younger crust there, which makes sense. We build margins out towards the active margin. The other option they offer is that as you get closer towards the trench, you have thinner crust. And so this would cause that same kind of trend towards more isotopically evolved signatures inboard of the trench. Okay, the third mechanism, we've already looked at an example of this. So this would just be mixing, remelting, right? And this is an example from the anti-atlas. They're looking at it for provenance results. But we see this vertical mixing array at 600 MA. So again, let's ask that same question that we asked a few slides ago. What about these up here? Could these just be remelting of old crust, or do we need some new inputs to our system? Can we get these positive values without bringing in some new juvenile components?
I see need new.
Huh?
Need new.
Yeah.
Juvenile dash. Is the juvenile dash line new crust?
Is the juvenile dash line new crust?
See, and then a hand or red dashed line. Is that juvenile crust?
Oh, this red dash line. That is a good question. I do not remember what they call that red dash line. I thought, yeah, that's just the error bars on depleted mantle compositions. So this kind of red hue color is just the uncertainty on that depleted mantle composition through time.
Yeah, we're getting a lot of answers. Basically, need new juvenile.
That's what I would say too. Yeah, so we have remelting of some old stuff, but we've also got some new input.
Maybe I'll just ask the question, what do you guys think about calculating TDM from all of those analyses that are along the word mixing? That would suggest there was mantle extraction pretty much continuously from 2 billion years ago until 600 million years ago, right?
Can we do that? Just make a histogram of it and call it a day? I hope you're all making George very happy by saying, no, George, don't do that. Stop.
Yeah, but they're thinking it. Okay, let's press on.
Okay, so obviously, a lot of what we do in this lab, in our lab, is detrital zircon geochronology. And, I think a problem that comes out a lot in detrital zircon geochronology is you get these huge data sets where in terms of age populations, they might not be diagnostic at all, right? So you might have the same age source region all around. So this is a problem in, say, the Pyrenees. But you might have really distinctive hafnium compositions. So here's an example over in kind of the Arabian, Nubian Shield area, where we see that these different different hafnium populations take up very different areas in hafnium space. And so while a detrital zircon age spectra alone might not be a diagnostic tool, these kind of different spread in hafnium space could be a really helpful fingerprint if you were looking at, say, a detrital sandstone to say, oh, did this come from the Cadomium arc? Oh yeah, it has these really negative epsilon hafnium signatures. It must be coming from there, versus if I see a broadly distributed age with only pretty juvenile signatures, I might attribute it to perhaps the Arabian or Nubian shields. Okay, so here's another data set for you guys to work through. This is kind of a fun one. So this one's from South Australia, from the Ceduna River. And they basically take these samples from a Cretaceous delta system, and they use the hafnium fingerprint, the hafnium isotopic data as a fingerprint to say that the transcontinental river system that is there today probably didn't exist in the Cretaceous. But they don't actually do a whole lot to interpret kind of what these changes in hafnium mean through time. They basically say that things are more spread out here and less spread out here. So feel free to jump in, interpret their data. Let's see what you guys got. Anyone, let's take a stab at this one. What are we doing at 600 MA, 550 MA?
Looks like we have a collision suggestion.
Sure. Yeah, so we've got definitely an isotopic pull down, some remelting of existing crust. So I guess one of the things that I think is really important with these data sets, and something that I've done a lot of when I do my hafnium data, is trying to reconstruct where the arc is through time. Because if you go back to kind of the different options that we have for driving these pull downs, arc position might actually help you kind of narrow in on what's going on. Okay, any other thoughts on this one? What are we doing here? Are we going up towards more positive values?
Looks like we have a good suggestion, collision, then extension.
Yeah, sure, I like it. We need something to pull us down towards more evolved signatures and something to pull us back up. Okay, so here's an example from the Tian Shan where they basically take their hafnium data, they pull it back to depleted mantle, they make these sweet PDPs that show the depleted mantle extraction age. What do you guys think about this? Viable? They've drawn these yellow bars coming back to depleted mantle, turn those ages into a histogram, said that we have mantle extraction at 2.4, 1.4, 1.1 GA. So what did George say early in the course? Do we have one stage melting? Can we just calculate depleted mantle extraction ages based on hafnium if it's not on the depleted mantle?
Got a comment, the 2.5 is sketchy.
2.5 is sketchy. I'd say the 1.4 is sketchy. I'd say the 1.1 is sketchy.
See, we got another comment here. Might need a bit more constraint on whether those are actually correlated to their DM interpretations, such as a zircon population at the DM somewhere.
Yeah. Yeah, so it's, as George mentioned before, it's really tricky to calculate these extraction ages because we don't know whether these are one stage melting, right? That's what these, if you're doing something like this, that's what it assumes, one stage melting. And that's pretty rare. So perhaps, if you're going to calculate depleted or extraction ages, do so cautiously. this would be a pretty bold interpretation. George, anything to add here?
Nope, looks good.
Okay, so I don't want to hold this up too much. I know we're already 10 minutes over time. So with that in mind, make sure when you're doing these hafnium data sets, as George has mentioned, it's a really hard measurement to make. You need to make sure that you're going to a lab that makes these corrections appropriately and that uses standards that explore the variability in ytterbium and lutetium space. We always, in our lab, mount our standards with our unknown. We've already talked about kind of fractionation that you get across the tray if you mount them separately. Visit the lab, generate your own data, go to a lab with an existing methods paper. This is a kind of, suggestion from us, which is don't analyze all of your grains. For example, split stream, you're going to be getting too much data. You're going to lose some efficiency there because you are rate limited by the lutetium hafnium analysis, which is a much slower analysis. Don't calculate depleted mantle model ages. And if you do, interpret them cautiously. And, have folks at the lab check your data, make sure you're not doing anything too wonky. Yeah, so that's what I have for applications of hafnium. I know it's a little weird to talk about those different options for isotopic pull downs, but I think it's important to recognize, like, seeing these papers that are coming out, they almost always invoke one mechanism, and there's a bunch of different things that can cause that kind of change in hafnium isotopes. Okay, any questions for hafnium isotopes, or should we hand it over to Kurt to do some fun plotting? Or do we have a break? We have a break.
We have a break scheduled for right now. I'm sure people are, especially on the East Coast, I'm sure are ready for a break. It's getting a little later out there.
Yep.
Yeah, what do you